Hi everyone, in this video we're going to compute some examples we're going to look at some examples where we compute the vertical asymptotes given the function expression. So from the last video, where we left off was by saying that we have a vertical asymptote at the vertical line x equals a if as x gets closer and closer to a, the function either grows toward positive infinity, so this would look something like that. So as x is getting close to a, the function is growing and getting more and more vertical. Or as x is getting closer to a, the function is getting more and more negative. It's shooting toward negative infinity. So what we need to think about when we're trying to figure out where a vertical asymptote might be is which x values of a function are going to make the function really, really big or really, really small in the negative direction. So let's look at this one, 2x plus 1 over x plus 1. Well, this is just a fraction, right? So if you have a fraction, a over b, this will be big when b is small. So when b is close to 0. So 2x plus 1 over x plus 1 will be its biggest when x plus 1 is as close to 0 as possible. And so x plus 1 is going to be 0. X plus 1 equals 0 when x equals negative 1. So if we're looking for the domain is all reals such that x does not equal negative 1. But as we get close to negative 1, as the denominator is getting closer and closer to 0, the entire function should be getting really large. So let's look at the graph of this. We want to put it in parentheses, 2x plus 1 divided by x plus 1. Check out the graph. Yeah, so as we get closer and closer to negative 1 from the left, it shoots up toward positive infinity. As we get closer and closer to negative 1 from the right, it goes down to negative infinity. Because we'll be dividing by numbers closer and closer to 0. When we're actually at negative 1, there's no value because negative 1's not in the domain. We get an error in the table. So just to really hit this home, what is f of x when x is negative 1.000001, when it's very, very close to 1? So let's try. If we do 2 in the numerator, 2 times negative 1.000001 in the numerator, and then that's plus 1. Divide that by plugging in this number for x, negative 1.000001 plus 1. Well, what is this? A huge number. So this tells us we have a vertical asymptote at x equals negative 1. And we also observe that from the graph, because at negative 1, the graph looks like it starts to look like a vertical line. So here's another example, 4 over x squared plus 1. In this example, it was helpful to find the domain because it told us when the denominator was 0. So x squared plus 1 equals 0. Does that ever happen? No, never. So since the domain is all real numbers, no matter what we plug in for x, this is never going to get close to 0. We'll never be dividing by a small enough number to make this whole thing go off to infinity. And we can see that from the graph by doing 4 divided by x squared plus 1. Check out the graph. There's no vertical asymptote. This is its highest point when x is 0. So we have no vertical asymptotes. And that's because the denominator never gets close to 0. In this last example, you've seen this one before, 1 over x. That's our parent function. And we have a vertical asymptote at x equals 0. At x equals 0, because I'm covering up my writing. Sorry about that. We have a vertical asymptote at x equals 0 because as the x values get closer and closer to 0, we're dividing by very small numbers. F of x is either getting very large in the positive direction or very small in the negative. So let's write this down as a rule. So if this is our polynomial, our rational function, one polynomial divided by another, where they have no common factors. We'll look at an example in just a moment that shows why this is important. Then the graph of f has vertical asymptotes when d of x equals 0. So x equals a is a vertical asymptote if a is a 0 of d. So in these examples, we had a vertical asymptote at -1 because -1 was a 0 of the denominator. We didn't have any vertical asymptotes for this one because there are no zeros of the denominator. And x equals 0 was a vertical asymptote of this one because that was the 0 of the denominator. Now, why do we need this no common factors? Well, remember this example we did in the last video where we looked at x plus 2 times x plus 1 over x minus 6 times x plus 2, and we could cancel and get this function? Well, if we just use the zeros of the denominator, we would have assumed that there was a vertical asymptote at -2 and 6. But when I plug -2 into this function, I'm going to have something close to 0 in the denominator, sure. But I'll be able to cancel it with something close to 0 in the numerator. So this is the function I want to study, the simplified version, when I'm looking for asymptotes. So again, we can look at this function, y equals, in the numerator, x squared plus 3x plus 2, and in the denominator, x squared minus 4x minus 12. And we'll see that there's only a vertical asymptote at x equals 6 after looking at the zeros of the simplified version, because the value which would be close to 0 in the denominator cancels with the value that would be close to 0 in the numerator for x values close to -2. So it's really not difficult to find vertical asymptotes. The steps are 1, simplify, 2, find the zeros of the denominator. So these are almost the same steps as when you're finding the domain of a function, except you have to simplify first when you're finding the asymptotes. Something that is important to remember is that an asymptote is not part of the graph. We know that the graph is not defined when the denominator is 0 because those values are not in the domain. It's just a vertical line that the graph starts to look like as you get close to that point. So if we zoom way out here, let's go -100 to 100. At 6, where we have our vertical asymptote, the graph just starts to look vertical. It never crosses this line because there's no value defined at 6, but it starts to look vertical there. That's what it means to be a vertical asymptote. So later we'll see how these can be helpful in graphing, and in the next video we're going to talk about horizontal asymptotes. So I hope that these examples clarified some things, and really if you just follow the steps, simplify, and then find the zeros of the denominator, you'll be fine. So good luck with the problems, and let me know if you have any questions at all.